how to interpret a regression model in Rstudio. So you've run your multiple regression model in Rstudio and you're not sure what all these numbers mean. How do we interpret a regression model in Rstudio? Let's find out. Here's the output from a regression model in rstanarm. Let's begin with the formula that summarizes the model. We can see the outcome variable on the left of the tilde and the predictor and control variables on the right. In this example, the outcome variable is the length of hair. In this population, some people have long hair, others have short hair. We use the regression model to predict this variance. On the right, we have the predictor and control variables. Let's assume height is our predictor. We have a theory that tells us that taller people tend to have shorter hair. So height is our predictor variable, and age and the number of siblings are our control variables. Mathematically, there is no difference between predictors and control variables, but differentiating them helps us interpret the model, especially if you want to say something about causality, which is most of the time. We get an intercept and a coefficient for each variable. So each line in this table stands for a variable. Let's find the coefficient for our predictor variable, height. It's minus 1.0. To understand what this number means, we need to know how the outcome variable and the predictor variable are measured. Like the length of hair is measured in centimeters, and height is also measured in centimeters. In the model, Rstudio has created two people for us who are exactly the same, like perfect clones. They only differ in exactly one aspect, their height. Well, not quite perfect clones after all. Anyway, in the world of the model, we can create such near-perfect clones. Perhaps you've heard references to all other things being equal. That's just a different way to say near-perfect clone. All other things means all other things in the model. So here we have two people and they are exactly the same in the other variables in the model. Same age, same number of siblings. The only difference between the two people is that one of them is 1 centimeter taller than the other. Why 1 centimeter? Because we measured height in units of 1 centimeter. In the world of the models, if the hair of this person is say 20 centimeters long, the hair of that person is predicted to be 1.0 centimeters shorter. That's 19.0 centimeters. Shorter because minus 1.0 is a negative length. This is what the minus 1.0 means. Let's create a third person, all other things the same again, but 15 centimeters taller. Remember, when in the world of the model, we can do these things. If the hair of the first person is 20 centimeters, that third person is predicted to have 15 times 1.0 centimeters shorter hair, so 5 centimeters. So even though the coefficient may look small, it can describe a substantively large difference. Now, we're still in the world of the model, and everything comes with uncertainty. In the table, we have a standard error for every coefficient. The larger the standard error is relative to the coefficient, the less certain we are. So we always compare the standard error to the coefficient that goes with it. Here we have a coefficient for height, and here we have the standard error to go with. Here the coefficient for the number of siblings, one of the control variables, and here the standard error to go with. If the standard error is too large, we probably don't want to say anything. We're just not sure. What's too large? That's a judgment you'll have to make. Many draw the line at around the point where the coefficient, in absolute terms, is twice as large as the standard error. But that's still a judgment, and you probably want to stay clear of arbitrary fixed cutoffs.